In this video, we'll form a general solution and then we'll find the actual solution that passes through these initial conditions here. So one thing at a time, the first thing we'll do is first come up with a general solution. Now this is a second order linear differential equation with constant coefficients, which means that the assumption is that y is equal to e to the lambda t. So when we do that, we end up with the characteristic equation lambda squared plus 6 lambda plus 9 equals 0, which means we have lambda plus 3 quantity squared equals 0, which is a repeated root. Lambda equals -3 repeated, which means that our general solution is c1e to the -3t, again following that assumption that lambda equals -3. And the other solution has an e to the -3t as well, but to show that it's repeated, we have to get that second solution in there. Turns out that it's a t that gets multiplied, and that's what makes those linearly independent. So now our job is to figure out what values of c1 and c2 have to be used so that the curve itself passes through 0, 1, and the derivative passes through 0, 2. So this is y. So this means that y at 0 is equal to c1 e to the 0 plus c2 times 0 e to the 0, and I want that to be 1. So that means this essentially crosses out, so we get that c1 is equal to 1. Beautiful. We got an answer off of that one. For the other one, though, we have to take the derivative first, so we first need to know what y prime is. Now, I'm going to leave c1 and I'm going to leave c1 anyway in there, just so we can plug it in later, just to keep the placeholders going. So the derivative is -3 c1 e to the -3t plus, now this one is going to require, I'm going to use a different color here, this one's going to require a product rule because you have a t times e to the -3t. So the derivative of c2 times t is c2 and times the second, which is e to the -3t, plus the first, c2t, times the derivative of the second, which is e to the -3t, times a -3. So I'm going to change this to a -3 out here. And since this is pretty much the end of the road for derivatives, we can just use this without having to combine like terms, although there are no like terms to combine, so I guess that doesn't matter anyway. So we have, y prime at 0 is equal to -3 c1 times e to the 0, which is 1, plus c2 times e to the 0, which is 1, minus 3 c2, t is 0, e to the 0, so this whole term just goes away. And we end up with -3 c1 plus c2, and that's supposed to be equal to 2, which is from up there. Now, we already found that c1 is supposed to be 1. So that means that c2 is equal to 5. So now that means we have enough ammo to write our actual solution, which is y equals c1 is 1, so that's e to the -3t, plus c2, 5, te to the -3t, which, if you want to impress your instructors, you could factor out e to the -3t if you want to. That just makes the solution look a little bit more concise. Either one of those is perfectly acceptable, though. So there is solving a differential equation and applying an initial condition. And that's pretty much how they usually go. We don't always get lucky enough to have like one of them cancel out on the way, but so at the worst, we're going to have a system of equations to solve. I'll handle that in another video for you, and then that's going to basically be getting us going for solving these equations. We're going to be able to get into applications soon. So again, thanks so much for watching.